Now, I've got to be honest, I'm as guilty as the next person sometimes in not reading a question carefully enough and just seeing the equation and going straight into solving it. But let's just read it. So a sample of bacteria is sealed in a sealed container is being studied, and the number of bacteria P in thousands, and that's the bit I'm trying to just highlight here, is modeled by this differential equation, where T is the time in hours after the start of the study. Time in hours. Actually, that doesn't end up being important. But they say initially there are exactly 5,000 bacteria in the container, and that means when T is 0, P is going to equal 5. Because remember, P is measured in thousands. We're asked to determine, according to the model, the number of bacteria in the container 8 hours after the start of the study. So when T is 8. Okay, we're going to work out a general solution to this first order differential equation, and then we're going to get a particular solution. And this is an integrating factor question. So let's write it in the form, well, dy by dx plus y times some polynomial of x equals q of x. And it can be shown that if you multiply, so I don't know why I'm writing p of x there, if you multiply by an integrating factor e to the integral of p of x, then you can rewrite the left-hand side as like a single derivative. Okay, I've proven it in other videos. We're just going to go with it here. It's something that once you practiced it a lot, yeah, you're into that mode. But you've got to get it into this form first. So let's divide through by 1 plus t. I'm therefore going to get p times 1 over 1 plus t. And that's going to equal t to the half because it cancels out there. And then my integrating factor is going to be e to the integral of 1 over 1 plus t with respect to t. This ends up becoming e to the ln 1 plus t. And the e and the ln cancel, so actually we're going to be timesing through by 1 plus t. And in fact, we get back to the very beginning. But, you wouldn't know that to start with. So we can now take this very beginning bit and rewrite it as d by dt of p times 1 plus t, and that's equal to t to the half 1 plus t. And you can check it. If you differentiate this using the product rule, you're going to get dp by dt times 1 plus t plus p times the derivative of 1 plus t, which is just 1. So we get back to that. Okay, let's integrate. Integrate both sides with respect to t. The left-hand side is simply going to become p times 1 plus t because we're differentiating, then we're integrating, we just get back to the original. And then to integrate this, you do not need to use integration by parts. I know it's a product, but let's just multiply out the brackets. T to the half plus t to the 3 over 2. That's the way to go. Then raise the power by 1, divide by the new power. And the same here. And then you've got your arbitrary constant. So then P will equal 2t to the 3 over 2 over 3 times 1 plus t plus 2t to the 5 over 2 over 5 1 plus t plus c over 1 plus t. And that is our that is our general solution. Remember, we're given this as our initial conditions. So let's sub them in, and that will allow us to find out c. And this ends up giving, well, we're going to set 5 equal to all of this. And actually, the first two terms just cancel. And the third term just becomes c divided by 1. C is 5. So our particular solution is very quick to get. P equals great. Now we're not quite done because actually we're asked to find the number of bacteria in the container 8 hours after the start of the study. So T equals 8, substitute it in, then just do it really carefully. P ends up equaling 10.2769. Remember that we then need to write it in thousands. It's 10.2769 thousand bacteria. So 10,277 bacteria to the nearest whole number. In the next part, we're asked to find, according to the model, the rate of change of bacteria in the container 4 hours after the start of the study. Now, I took a little look at this and I thought, oh, really? Do I really have to differentiate this? That's the quotient rule twice, and then sub in 4. And of course, you can do it that way, but here's a sneaky way. You can return to the differential equation and actually just get the derivative back in terms of p. No differentiation required. Incredible. So dp by dt is actually going to equal t to the half minus p over 1 plus t. So when t is equal to 4, then you just sub it into this one, just like you did with 8. P ends up being 4.62666. And then dp by dt will equal square root of 4 minus that 4.62666 divided by 5, and that ends up being 1.07466. So that is 1,074.66 bacteria per hour. That's our rate of growth. Let's just round it to 1075. I read in the answers that if you use the quotient rule, then you end up getting 1070, I think. So look, there is a range that's accepted. So good that method, for those 4 marks, rather than having to use the quotient rule like multiple times. Finally, state a limitation of the model. Okay, now it's not really talked about any assumptions here, so the limitation is in reference to our actual solution. And normally it's things like what happens when the time becomes large. So as time approaches infinity, that's not what I normally write down. Actually, this term here is going to approach infinity. I know we're going to divide by a bigger number, but the t to the 3 over 2 is gonna dominate. It's like, you can basically you can say, you know what, that is going to become insignificant when t approaches infinity. And so we're going to get 2/3 times t to the half from that. And then from this one, that's going to become insignificant. We're going to get t to the 3 over 2 times 2/5. But basically, p is going to approach infinity since the first 2 terms both approach infinity. Yeah, unlimited growth. Model not realistic. Okay, well done on this question and on the whole paper.